Hello and welcome back. In this video, I'm talking about how pair of entities are selected for collisions in my custom physics package for Unity ECS called Little Physics. Before we begin, please hit the like button, subscribe to this channel, and write down in the comments if you want me to make more videos on Unity ECS. A small correction to the last video. When talking about the native parallel multi-HashMap structure, I said that adding to it blocks all other threads. That's not true. What actually happens? The structure builds buckets associated with each index. Adding to the structure blocks that specific bucket from changing it in other threads, while leaving other buckets free to access. This is very similar to how my custom structure works. Now to today's video. From the last time, we have a spatial map filled with physics body indices. We store them in a custom data structure, which is basically 1D array. We also have an array of physics body data, containing physical information about the objects. I also added a simple job that spawns cubes in the position of cells taken by objects in the map. You saw that in my previous video. It helps me debug adding to the map. Collision detection can be divided into these major steps. Find unique pairs in all cells. Find if objects within that pair intersect with each other. Calculate linear and angular collision forces and push out power. Apply these forces to the object's transforms. I want the user of the package to have access to collision results of the system. We also want a form of map that tells us what collision an entity had in this frame. The collision information we want is the other entity's ID, the contact point of the collision, and the impulse. Now let's think about what operations the structure will need. First, iterate through each entity's collisions. Second, check when adding to the map whether the key value pair already exists. And 3, add a collision into the map by an object's ID in parallel, potentially without conflicts. Here I introduce a ListsArray structure, an array of lists. It has two metrics: array length, basically the list's count, and the list capacity, which cannot be exceeded. Inside, it has a simple 1D array with a fixed size of lists count multiplied by list capacity with a generic type t, and an array of counts for each list. This is the same as the custom structure I talked about in the last video, but this time it's generic, which lets me use it with types like collision data. The structure will block multiple threads that try to add to the same list. Internally, the block happens using the count array's value with corresponding index. Also, following Unity's convention for native parallel data structures, I added an sParallelWriter method and a nested ParallelWriter class with a single TryAdd method, a safe method that locks the list for parallel threads. For consistency, I'll replace the collision map information with the same structure with its generic type set to uint, the index of an object in a map. One problem we encounter here. We have one system that fills a map array, and another system that uses that array to fill its own structures. We also have a physics body data array and system that fills it and systems that are using it. So we need all the system to run in a correct order, and the structures need to exist before they are addressed by other systems. We would also need to have a reference to a common job handle used in all systems of the pipeline, because ECS job scheduler by default will not identify each job as using our custom data structure. For that, I created a Bootstrapper system. It creates all the data structures, then creates a settings singleton, then creates a singleton component, physics singleton, that holds references to the data structures as well as common job handle. This component is also used in the systems requiring those structures. I'll put it in onCreate require for update so that all those systems run only after the data structures are created. At the moment, our map has each entity saved in multiple cells. Let's try and find unique pairs on the map. For now, let's store pairs in a lists array of uint. The first index will be the entity index, and the list will contain paired entities. The structure will only exist in the collision detection system, so there is no need to reference it in physics singleton. To solve this problem, we have two major approaches. Entity first approach. We run a job for each entity on the scene, and for each entity, we run through each cell it takes. Within each cell, we get the neighbor entity index, check if that index already exists in the paired list of that entity, and if it doesn't, we add it to the map. Cell first approach. We run a job for each cell of the grid. Within that, we loop through the cell content, and within that loop, we loop again to build a pair. Then, same as before, we check if the pair exists, and if not, we add it to the map. One general advantage of the first approach over the second. Remember how our structure blocks execution when two lists of the same index are edited. That isn't a problem for the first approach. Each job works on each entity and fills only the list of collisions related to that entity. But for the second approach, each job works on a cell, so thread locks are inevitable. With that in mind, let's build a spreadsheet and see which approach is better in terms of number of operations. Let's first include another limitation, max pairs per entity. This value tells us how many possible pairs each entity can have. It reflects possible pairs, entities sharing the same cell before the actual intersection calculation. This limitation exists so the system won't blow up with large numbers and to keep data organized. Approach 1 complexity. Number of entities multiplied by maximum cell taken by one entity, multiplied by number of entities in one cell, multiplied by max pair per entity. The last factor is added since when adding each potential pair, we need to check if it's not yet added. Approach 2 complexity. Number of cells multiplied by number of entities in one cell, power 2. Since the check is symmetrical, so each pair is checked only once. Multiplied by max pairs per entity, to check if it already exists. And here we can see that we don't have a concrete answer on which approach is better. Depending on cells count or the entities count, each one of them can either be good or bad. So why not use both? We just need to calculate coefficients based on complexity and see which one is better. By removing common multipliers, max pair per entity and number of entities in one cell, we get a simplified formula. Considering that the entities approach is faster in terms of adding and checking indices, we want to multiply it by some coefficient. I chose 2. So the final formula is this. The true result would mean that we would choose a cell-first approach. As I said, the cell-based approach requires writing to be possible in multi-threaded access, adding an index to the list whilst checking that it's not already there. For that, I added another nested type on ListsArray, ParallelUniqueWriter. With a TryAdd unique method that locks the list associated with an entity index and runs through it looking for a specific value. Normally, if you want to compare values of some generic type, that type needs to be comparable. But since our case this type will only be needed for uint values, we can use the memcmp method, which compares values bit by bit. To simplify both approaches, we'll skip all pairs while the first entity index greater or equal than the second. This will halve the amount of checks. One more optimization worth noting about the entities approach. When iterating through the cells taken by an entity, repeating the same operation used when filling the map, calculating what cells the entity occupies. We can save that intermediate result into a structure called AABB, or Access Aligned Bounding Box, which holds the position of the map, the size, and the total map size. This can be calculated at the start of the pipeline right after importing components into the array of data, and stored directly in physics body data. And here's the intermediate performance result. So that's it for today. In the next video, I'm going to talk about the intersections and collisions calculations. Don't forget to hit the like button, subscribe, and I'm going to see you in the next time.